Okay, I think I apologize for not look into any, conflicts of this meeting. Our normal meeting hour is 3:30, but since we have a speaker from Europe, and that is just too late, so we normally move a little bit earlier. But today, I guess there are a group of people who are actually in the EIC meeting, and that's why we postponed this talk about 10 minutes later, just hoping in case that some of them will join us later and still catch some part of this talk. So I'm really happy to have our today's speaker, Dr. You Zhou. And well, many of them, you probably know him well because he's part of the ALICE collaboration. And you got his master's degree in 2010 from Central China Normal University. And then at 2014, he got his PhD from NICAF. And after that, I think he became a postdoc at Niels Bohr Institute. And later on, he became, at least from 2017, he became Carlsberg Research Fellow there. And since 2018, he's a tenure track assistant professor. Oh, he was a tenure assistant professor at Lund University, Sweden, but he did not take it, I say. And then he's now assistant professor at Niels Bohr Institute, University of Copenhagen. And today, he's going to talk about multi-particle correlation for a new decade of QGT studies. Please go ahead.
Sure, thanks, Shannon, for the invitation as well as the introduction. So I try to have a full screen of the slides. Could you tell me is the full screen already?
Yeah.
Okay, excellent. So it's my really great pleasure to give the seminar at HIT seminar. It has been quite a while that I haven't visited Berkeley, and hopefully we will have a chance very soon to talk to each other in person. So today I will talk about multi-particle correlation for the new decade of QGP study. So everything starts from the central topic of the heavy ion physics, or we try to understand the so-called evolution of the little Big Bang. So for heavy ion collision, we collide at the LHC, we collide the lead ion or xenon ion at almost the speed of light. There will be some initial condition which will quickly move to the Quark-Gluon Plasma phase. And, and these quarks and gluons will be combined to hadrons in the process of hadronization. And then the hadrons, the pion, cation, proton, etc., will interact with each other until the certain time called freeze out. Then those particles, those hadrons will escape from the system and can be catched by the detector like eddies. For the entire process, it's quite complicated and there are a lot of unknown parts in experiments. So what we usually do is we try to develop theoretical model, or especially hybrid theoretical model, to simulate each process. For instance, for initial condition, we have some initial sane model like Toronto IP plasma. And for the QGP dynamics, we have some hydrodynamic simulations from by Vishnu or shell whisk or glass or music. And for the final hadronic interactions, we also have the transport model like URQMD or SMASH. And so what we do in the end is we try to compare the results in the final state calculation to the experimental measurements and try to extract the information about the early dynamics during the QGP phase, or try to understand what's going on in a complicated initial conditions. So this is what we usually do in heavy ion physics, in my opinion. So one of the golden probe or very popular probe for the study of the QGP is the anisotropic flow phenomena, which of course many people are very familiar with. The central idea is for non-central heavy ion collisions, you have the overlapped region between the two colliding nucleon. This initial spatial anisotropy will convolute into the final state of anisotropic particle expansion, which show a preferred direction of the expansion. So this final state anisotropic particle expansion is known as anisotropic flow. And the magnitude of this anisotropic flow could reflect the size of the initial anisotropic coefficient or eccentricity, and also the transport property of the QGP. So basically what we want to do is we measure the final state anisotropic particle expansion in terms of Vn coefficient. And then we use the size of the Vn to compare to a theoretical model and try to extract the information about the transport coefficient, including shear and bulk viscosity of the Quark-Gluon plasma. So this is basically the definition of Vn. So of course, if you look at the definition of Vn, this is basically the azimuthal angle of the produced particle with respect to a common symmetry plane. So if you want to measure V2, you look at azimuthal angle with respect to psi2. Unfortunately, the psi2 is unknown in experiment. So what we hope to do, or what have been proposed in the past more than 20 years ago, is look at particle azimuthal correlations. So now if you have two particle correlation, you have phi1 and phi2. If you do a simple math, you can end up with the Vn square, which is RMS root mean square value of the Vn distribution without knowing the psi, the flow symmetry plane event by event. So this is the idea behind the two particle correlation. And that's what we hope to get in experiments. However, the reality is more complicated than what we expect. What we really get, or actually get from the two particle azimuthal angle correlation experiments, including not only the Vn square, but also the delta 2, which is called the non-flow effect, which is a big contamination of the flow analysis. Non-flow effects are basically azimuthal angle correlation, not correlated with the flow symmetry plane psi n. Some of the major sources are resonance decays or jets, which are of course not associated with a flow symmetry plane. So roughly speaking, the size of the non-flow for two particle correlation is roughly 1 over m at the level of 1 over m. So imagine that if you have a peripheral or semi-peripheral collision, well, the m is not very large, then the non-flow effect could be significant. So this has been very well known that two particle correlation will be biased by non-flow effect. So in order to get rid of this non-flow effect and really compare the true flow effect to a model, which normally do not have the non-flow effect, multi-particle cumulant have been proposed already more than 20 years ago. One example is 4-particle cumulants. When you have correlated 4-particle, phi1, phi2, phi3, phi4, you have a true 4-particle correlation, but you also have contains the low order 2-particle correlation, the internal correlation. For example, you have correlation between phi1, phi3, phi2, phi4, or if the other pair, phi1, phi4, phi2, phi3. And then you, in order to measure the true 4-particle correlation or genuine 4-particle correlation, you want to subtract the low order correlation between 2 particles. So that's what we do, is subtract 1, 3 to 4, and also 1, 4 to 3. So in the end, you end up with a Vn minus Vn power 4 plus a non-flow, which is a non-flow of 4-particle correlation. Usually it is at the level of 1 over m to the cube, 1 cube. So in the side, so if you think about m, if the m is not very small in heavy ion collision, normally non-flow is almost negligible for heavy ion physics if you do 4-particle cumulant. Using the similar idea, you can even extend to high order cumulant V26 or V28. And this has been well known, and in fact also developed by former colleagues in Berkeley, especially Art and collaborators, that for a Bayesian type of flow fluctuation, in the case of sigma, the flow fluctuation is much smaller than the Vn, the mean Vn. We get the approximation of Vn square equals the mean Vn square plus the flow fluctuation plus non-flow, while all the other high order cumulants, V2, Vn4, Vn6, Vn8, they are roughly equal Vn square minus sigma Vn square, which means the 2 and 4 particle or 2 and multi-particle cumulant have different sensitivity to the flow and flow fluctuations. The contribution is positive in 2 particle, and it is negative for the high order cumulant. Okay, this has been well known. Now, if we look at the data, so in the left-hand side, I show the flow measurements as a function of centrality in the light collision at 5.02 TeV, as well as the measurements at low energy. So if you can see the results are in red, which is V2, the blue is V3, the green is V4, then you can clearly see V2 larger than V3, larger than V4, as we expect from the hydrodynamic evolution. In addition, we talked about earlier that the V22, V24, V26, V28 have different sensitivity and to a flow fluctuation, which is positive for two particle and negative for high order cumulants. That's why you can clearly see a deviation between the red and for instance, in the gray cross with V24, and then the orange diamond is V26, and then also V28. This basically explains that the difference between two and multi-particle cumulants can be well explained by flow fluctuations. In addition, you can also see the comparison to hydrodynamic prediction before we had the first Alice data measurements. And there's a very good agreement between the experimental data and theoretical model prediction, which further confirm that the flow measurements at the LHC shows that the Quark-Gluon Plasma behave still like a perfect fluid at the top LHC energy. In the right-hand side is the measurements which we did in 2017, 2018 in xenon-xenon collision at 5.44 TeV. Again, very good agreement can be seen between hydrodynamics and theoretical hydrodynamics and also experimental data for V2, V3, and V4. So those are simple measurements for Vn. And now, if you talk about V2 and higher order cumulants, so if you have V2, Vn2, Vn4, Vn6, Vn8, you can reconstruct the underlying probability density function PVN and extract the PVN distribution in the final state, which tells you how does V2 fluctuate event by event. And then the black shadow shows the Alice data, so the PV2 distribution, while the colorful shadows shows the different theoretical model predictions. So you can see here, for instance, the AMPT initial condition plus IE by E Vishnu hydrodynamic calculation somehow gave a wider PV2 distribution and couldn't describe the data, while the one from Trento initial condition plus IE by Vishnu describe the data better. And now if you think about the V2 itself, so V2 and V3 are driven from initial conditions, eccentricity epsilon 2 and epsilon 3. And we know in the past that V2 and V3 have linear response to eccentricity epsilon 2 and epsilon 3. So in that sense, if we look at PV2 distribution and we scale by the mean V2, then we expect that the underlying PDF will be the same as eccentricity fluctuations scaled P epsilon n scaled by the mean eccentricity. This has been tested with hydrodynamic framework from IP Plasma initial condition as well as IP Plasma plus Munich for the final state hydrodynamic calculation. So basically, with such a measurement in data, we can use the data to directly constrain the eccentricity fluctuations from the initial set models. So here I try to ask Giuliano for some help, who also just gave a HIT seminar, I guess last week. He actually nicely calculated these PV2 P eccentricity divided by mean eccentricity distribution from different initial state model, including Traditon for the Bayesian analysis, Trento 16-tuned, IP Plasma, and Jetscape. And you can see that Jetscape somehow gave you a bit narrow distribution for the PVN. And considering that there's a good agreement between these Trento 2016-tuned with respect to Alice data, so it is very likely that Jetscape will not be able to describe the Alice data. So now I describe the V22, V24, and V32, V34. And then for this well-known global Bayesian analysis, which is based on the hybrid hydrodynamic framework, they have the tuned parameter for initial state calculation, initial condition from Trento. They also have other parameters for the Edelweiss, and then they fit the Alice particle spectra, mean PT, the flow and flow fluctuations, and also mean PD fluctuations. They can extract the initial condition in terms of a P value for the from Trento, and they can also extract information from about the Edelweiss and Edelweiss as a function of temperature. And similarly, for the latest paper from Jetscape collaboration, they also try to fit the particles, or not particle spectra, the d and dy, as well as a mean PT for identified particles. And in addition, they try to fit the V2, V3, V4. But please note that here in this paper, they haven't used the V24, which has been used in this Duke Bayesian analysis, which means the flow fluctuation hasn't been considered in such a global constraint. And that perhaps also explained that if you go back to the previous slide, J-scape somehow could not really describe the relative fluctuation of the flow. So in the previous slides, I talked about the flow higher harmonic. So the higher order cumulants, for instance, the 4-particle cumulant of CN4 for the single harmonic. Now you can also think about, so why you only stick to the same harmonic n? So can I change it to the other harmonic? In fact, you can, as long as you ensure the symmetry. So now I have the correlation between n phi 1, n phi 2, n phi 3, n phi 4. So I have this 4-particle correlation. Now I want to subtract the low order correlation to get the genuine 4-particle correlation or 4-particle cumulant. So what I do is I try to find the internal correlation between them. Well, I have m phi 1, m phi 3, and also n phi 2, n phi 4. So I try to subtract the, sorry, there should be a times. So I have these additional two particle pairs of correlation that I need to subtract. And in the end, I can construct a new 4-particle cumulant that can be used to study the correlation between different order flow coefficient, Vm squared and Vn squared. This is what my colleague and myself proposed 7 years ago and called Symmetric Cumulant, which can be used to quantitatively study the correlation between different order flow coefficient. So why this observer is very interesting. So now, in addition to the so-called symmetric cumulants, we normalized by the Vn square and Vn square, as shown in the title of the y-axis, and we can see a very interesting result presented here. So what we have in this figure, if you look at the red points, this is the normalized symmetric cumulants between V2 and V4, which is positive for the entire centrality, which means the V2 and V4 are positively correlated. That means for a single event, if your V2 is higher than event average V2, then for this particular event, its V4 is very likely also larger than the event average V4. In contrast, if you look at the correlation between V2 and V3, it is negative. In the sense, V2 and V3 are anti-correlated with each other or have a negative correlation. That means if you, for a single event, if your V2 is larger than event average V2, then for this event, its V3 will be smaller than event average V3. So in addition, we also show the comparison to hydrodynamic calculation. And you can see that when you change the eta of S as a function of temperature, there's a big change in hydrodynamic calculation, which means the correlation between V2 and V4 is very sensitive to the eta of S as a function of temperature. Therefore, you can use the Alice data to really try to probe the time evolution of the eta of S. While if you look at blue, it's also very interesting because all the curves, no matter how different eta of S they set, all the curves fall into a universal line. So in order to understand these results, in 2017, Hui Chao and me and Hui Chao's group try to have this calculation. So what we do is, again, the normalized symmetric cumulants of 3, 2, which measure the correlation between V2 and V3 in both final state and in initial state. So again, assume the V2 and V3 are linearly correlated with eccentricity epsilon 2 and epsilon 3. Then we would expect this simple equation that the final state normalized symmetric cumulant between 3, 2 will be equivalent to the normalized symmetric cumulant for eccentricity epsilon 2 and epsilon 3. Then we should expect the agreement between the two in model calculation. That's basically what we see. If you are using Glauber initial condition, Monte Carlo Ki and CGC initial condition, or AMPT initial condition for central and semi-central collision, you will see a rough agreement between the two, which confirm that you can, which confirm that a normalized symmetric cumulus is insensitive to the eta of S as function of temperature, as shown in the left-hand side, while it is very sensitive to the initial conditions, or basically reflect the initial condition, the correlation between epsilon2 and epsilon3. And we can use the normalized symmetric cumulants to probe the initial correlation between epsilon2 and epsilon3. Now, we also, last year, we also have the new measurements based on the LHC round 2 data, which is very precise. So if you look at the black points, solid black points, it's a measurement of normalized symmetric cumulants 3-2 in 5 TeV as function of centrality. And you see the error bar for both static and systematic uncertainty have been largely suppressed compared to the round 1 measurements. And in addition, we compare a different theoretical model from both the final state calculation as well as initial state calculation. And again, here we can roughly confirm that there's a very good agreement between the final state calculation and the initial state calculation within the same model, which means for normalized symmetric cumulant, it again reflects the initial state eccentricity correlations. And then the Alice data is, if you look at the ratio between hydro and data, the red shadow, which is Trento initial condition plus temperature dependent of eta of S, based on the Duke 2016 tuned, describe the data better than the AMPT initial condition plus basically the AMPT initial condition. So in the right-hand side, I also get the help from—
What is your definition of NSC? What is the NSC? I missed that.
So this is a correlation between V2 square, V3 square.
I know, but normalized. I said
yeah, sorry.
Okay.
It's a normalized symmetric cumulant.
Okay.
So we divide by V2 square, V3 square.
Okay, sorry.
So if you do the normalization, then it will be insensitive to the magnitude of V2 or V3. So it doesn't matter whether the data, the model can describe V2 or V3 itself. It will be used to probe the relative correlation between V2 and V3. Or in this sense, eccentricity epsilon2 and epsilon3. So in the right-hand side, I also show you the initial state calculation, which is very interesting, because if you look at just remind you, in the left-hand side, Trento works the best, right? This is Trento 2016 tune, which is equivalent to the black shadow, the black lines that we see in the right-hand side. And then if you look at the Jetscape calculation, right? For centrality around 60%, they quickly change the line, change the sign to positive, which is clearly not seen in data. I mean, if you look at the result in centrality 50 to 60%, it is, I guess, minus 1.6, something like that. While if you look at Jetscape, it's around 0. And then if you look at IP plasma calculation for the initial state, it is below minus 0.2, which is clearly overestimate the size of the negative correlation. So from here, I can almost predict that Jetscape and IP plasma will fail to describe the NSC 3-2, no matter which eta of S or zeta of S they apply in the hydrodynamic code. So now the question is, now we can make the correlation between V2, V3 to the second moment. Can we do a general correlation between any arbitrary order of Vn, Vn, and also the correlation between more than 2 flow coefficients? So not only V2, V3, but also perhaps V4. And this is a little bit more complicated. So if you want to probe the online PDF of the Vn, Vk, you need some tools. So in fact, this has been nicely summarized in one of the review papers from Jiang Yong in 2014. And he tried to highlight, if you want to calculate the correlation between multiple flow coefficients, you need to have some recursive formula. Otherwise, you have to derive them one by one. So for example, if you want to study the 6-particle cumulant with mixed harmonic, right? So you have, for example, you have 251 plus 252 plus 353 minus 254 minus 255 minus 653, complicated. The idea is you have a 6-particle correlation. You need to subtract all the low order correlation. So here you have a 2-4 correlation. Here you have a 2-4 correlation. Here you have 2-4, 2-4 correlation. All this correlation should be subtracted. And this is basically what we have in the formula. You can always use this idea to derive them one by one, which somehow seems a little bit silly and complicated and will give you some mistake. So what we do in last year is we have some generic algorithm based on recursive formula. And with the one small function, you can calculate multi-particle correlation. So no matter here, you change whatever 1, 2, 3, 4. If you, as soon as you put some number, you can use the formula to calculate the multi-particle correlation. And then the other thing is you do not know how to construct the multi-particle cumulant. In a sense, if you are able to calculate the 6-particle correlation, you do not know which kind of lower order correlation you need to subtract. And this can be done by the right-hand side function. Just call the function, you can get whatever multi-particle cumulant constructed in terms of C++ code. So if you for theoretical model calculation or experimental data, you just run a small function, you have everything. You don't need to download any complicated package. So one example is now, again, 4-particle correlation will be the same as the symmetric cumulant, but now I can construct a 6-particle cumulant with mixed harmonic. And this can be used to study the correlation between V2, now power 4, V3 square correlation, compared to the previous one, which is V2 square, V3 square. I can also use it to calculate 6-particle cumulant for the correlation between V2 square, V3 square, V4 square with 3 different harmonics, or even go to higher order of V2, but higher order of V3, etc. to the with 8-particle cumulant. So one example is again published in Alice by Alice last year. So what we did here is we have, in addition to V2 square, V3 square correlation, we have on the higher order, the V2 power 4, V3 and V3 square correlation. So now if you still remember the normalized symmetric cumulant, which may this V2 square, V3 square correlation, and there is positive, it's negative for the entire centrality. But then if you look at the higher order, the V2 power 4, V3 square correlation is positive. And if you go to even higher order, though, so now if you look at the orange points, they are V2 power 6, V3 square correlation. It is again negative. So somehow you have this sign change from negative to positive to negative for the 4, 6, 8-particle cumulants of the mixed harmonic, which is actually very similar with the previous flow study for the single harmonic, that if you look at 2, 4, 6, 8-particle cumulant, it's positive, negative sign. So in order to understand results, just remember that we said before, V2 and V3 are linearly correlated with eccentricity epsilon 2 and epsilon 3. So if we do these normalized measurements in the final state, we can expect that this will reflect the information from the initial state correlation between eccentricity epsilon 2 and epsilon 3, but to the higher order now. So this has been tested with in this paper published last year with Hui Chao and myself, that we can run the hydrodynamic calculation with IE by Vishnu with AMPD initial condition. We can also calculate calculate the initial state correlation between eccentricity epsilon 2 and epsilon 3 to the different order. You can see a rough agreement between the two, which again tells you that for this normalized mixed harmonic cumulant between V2 and V3, it basically reflects the correlation between eccentricity epsilon 2 and epsilon 3. So what I want to show you, say in the end, is the experimental data presented in the left-hand side could provide direct constraints on the correlation of any moments of eccentricity coefficient from initial state model, which haven't been studied before. So now you can also ask, so about the other correlation. So one example I want to put it here is I have M phi 1 correlate, M phi 1, N phi 2, K phi 3. So 3 different harmonics. So can I also make something out of it? Yes. So if we play a bit of the mathematics, then it end up with the correlation between Vn square, Vn square, Vk square, and the cosine term of this complicated thing. This is actually the so-called flow symmetry plane correlation, or people also call it the event plane correlation. So now assume I have this observable row. I have the numerator, which is complicated, but I have a denominator which contains only the flow coefficient. So I can roughly cancel out most of the contribution from Vn coefficient, and what's left is a pure event plane correlation or flow symmetry plane correlation. So one example, if I calculate rho 422, it will give me the correlation between psi 2 and psi 4, the second order and the fourth order flow symmetry plane correlation, which has been done in the right-hand side. And all these event plane correlations have been also studied in great details and compared to different hydrodynamic model with different initial condition and with different intervals. And in fact, in a recent Bayesian analysis paper, they try to include not only the VN standard VN coefficient, but also complicated study for flow observable, including the normalized symmetric cumulant or the nonlinear flow, the flow symmetry plane correlations. And they try to claim that they have a better constraint on the initial state model as well as the QGP properties than the Bayesian analysis with only a VN coefficient itself. So for more details, please refer to these two publications. So far I only talked about azimuthal angle correlation, which is very powerful and show you a lot of new information. And in last few years, we really have a great study of the event by event fluctuation in the final state, as well as the good probe to the initial eccentricity fluctuations. So one of the relatively new ideas is a new type of correlation, not only between azimuthal angle, but now we introduce the PT into the correlation. And actually this is a good idea because both mean PT and VN have been used as a baseline for the experimental input for the global Bayesian analysis. So in principle, both VN and mean PT have been used in Bayesian analysis to extract the initial condition and also the QGP properties. So now if we think about the anisotropic flow, it reflects the shape of the fireball we are talking about. And the mean PT basically is sensitive to the size of the fireball. So now if you study the correlation, if you can find a way to study the correlation between VN and mean PT, they have a way to probe the initial state correlation between the shape and the size. And I believe this has been discussed in Juliana's seminar last week, that a new correlator, the rho V2 VN square PT correlation has been proposed in 2017 by Bozek, which allows to really study quantitatively the correlation between VN and PT. So the assumption is, again, VN is proportional to eccentricity and mean PT is proportional to the average energy density profile. Then we would expect that the final state correlation between VN and mean PT will be equivalent to the initial state correlation between eccentricity coefficient and the average entropy density. So then what we can do is we can confirm if this is true. So we can compare the rho measurements in the final state to the different initial state calculation and see if we can directly constrain the initial state model. So this idea has been validated in the right-hand side. So here I show you basically some final state hydrodynamic calculation as well as initial state calculation presented by this shadow about the dashed line. So if you just pick up one model, let's say Tradigen, we haven't discussed so much. This is a model Bayesian analysis done by our Dutch colleagues from Utrecht. The black shadow show you the final state Tradigen calculation, while the black lines show you the initial state calculation with eccentricity, etc. And you can see there's a very good agreement between the final state and initial state, which means that we can really use the experimental data to directly constrain the correlation between eccentricity, the size, and the shape of the initial state profile. So now I present you the latest measurements which submitted to PIL the end of last year, still within the review. So what we see is there's positive results of V2 mean PT correlation, and there's a very weak centrality dependence, as you can see in the black point. And then we also compare to the two different hydrodynamic calculation, IP plasma plus music plus European D, as well as the USB hydro based on the Toronto initial condition 2016 tuned. And you can see there's a very big difference actually between these two. So despite the fact that both IP plasma plus music plus European D and the USB hydro could describe VN and mean PT individually, they cannot really describe quantitatively the new Alice data for the correlation between V2 and mean PT. And also we see a huge difference between the two theoretical model calculations, which normally they do both well work, and now we see a big difference. So we try to understand what's going on. So now allow me to add more calculation, which make this figure a little bit mess. So I will try to guide this discussion again. So now I add two more calculations. One is from Traditon initial state calculation in the black -9, and Traditon final state calculation in the black box, black box. And also I add the Jetscape initial state calculation showed by this greenish -9, and also the green shadow for the final state Jetscape calculation. So what we can see is for most of these calculations, Traditon, Jetscape, VSB, Hydro, they are all based on the Trento initial condition. They show a very strong centrality dependence, show a strong decreasing trend toward more peripheral collision. And clearly the results from this hydrodynamic calculation are far away from the edit data point. So now, if you want to talk about the difference between IP Plasma-based calculation and Trento-based calculation, you would wonder, so why is there such a difference? Is it due to some pure geometrical effect, or due to some potential contribution from initial momentum and anisotropy driven from color class condensate that implemented in IP Plasma initial set model? So now I also add one more calculation from IP Plasma, but with the final state effect only, if you look at this pinkish shadow. And then if you compare to the final state effect only to the full IP Plasma simulation, the only potential difference will tell you the contribution from CGC. But if you look at this figure, basically within uncertainty, you don't really see any difference. That tells you that the potential initial momentum anisotropy from CGC will not play a significant role for the centrality up to 60%. And the difference between IP Plasma calculation and Trento are mainly due to some geometrical effect. So now if we move to row 3, which studied the correlation between V3 and mean PT, you can see the Alice data point is positive and show you a small increasing trend toward more peripheral collision. While if you look at the calculation, for instance, from Jetscape, it changed from positive to negative for centrality above 10% already. While the Traditon calculation, again, based on Trento initial condition, shows a decreasing trend and then become negative for centrality above 20%. And those two calculations are quite different from what we see in data. While if you look at IP Plasma, again, it quantitatively describes the data for centrality up to almost 50%. So in fact, we also have quite some discussion with Bion and Chun about this IP Plasma for the final state effect on the FSE calculation, because if you go to very peripheral collision centrality, not even very, it's a centrality 50 to 60%, you can see a significant difference between the final state effect only and for IP Plasma calculation. And what we understand before is if there's a significant difference, that's probably due to some CGC contribution. And we are still wondering if this is the real understanding of such a difference, or there are some other effects that they should understand or further investigate within the IP Plasma model. So actually, in the beginning of this year, there's a new paper submitted published by Giuliano and collaborator in PRL. So what they find is previously we compared the Alice data to a different model, the IP Plasma plus immunity plus UKMD, VSB Hydro, Traditon, Jetscape, etc. What they found is, in fact, these centrality dependence or the magnitude of this correlation between V2 and PT follow the order of the size of the nucleon, which is 0.4 for IP Plasma, 0.5 for this 2016 tuned USB Hydro, and roughly 0.7 for Traditon and 1.1 for Jetscape. So the nucleon size is so large, which leads a large deviation between the Jetscape hydrodynamic calculation from data. And within IP Plasma, they also tested that if you change the nucleon size, indeed you get a strong centrality dependence, and you can see a larger and larger deviation from the Alice data. However, at the moment, it's still unclear whether some other differences between the Trento initial condition and IP Plasma will play some role. For instance, there's a different treatment for the signal function, which means no matter which p-value you apply, the signal function in Trento and IP Plasma will never be equivalent. And there will be some other consideration, for example, the pre-hydrodynamic phase and also the subnucleon structure, which has been used in different Bayesian analysis. So now if we go back to our big picture that we would like to have using the Bayesian analysis to extract the information about the Quark-Gluon plasma. And most of these Bayesian analyses are using the Trento initial condition plus a hydro code plus a final state interaction. Now, the question is, in the previous slide, you find that most of the existing Bayesian analysis failed because of the very large nucleon size they used from the mean PT and VN individually. And the question is, if this initial condition does not allow you to describe the data properly, how about extract the eta of S and zeta of S you extract from the global Bayesian analysis? Do they still represent the best understanding of the QGP so far, or it needs to reinvestigate after better tuned of the initial condition? So now I want to show you the potential, actually the recent developments and also the potential future. So in fact, in the direction of the azimuthal angle multi-particle correlation, there have been a lot of activity in the standard area of flow study. So we studied the fluctuation of VN coefficient, which tells you how does the VN fluctuate event by event. And we also studied the flow symmetry plane, which tells you how does psi n fluctuate in different kinematic region, which can be done by this decorrelation of flow vector study. And we also discussed in this seminar about how do the correlation, how a correlation between VN and VN coefficient, and also how do the flow symmetry plane correlation tell us about anything about Quark-Gluon plasma. This has been done in great details. However, there's another dimension about the multi-particle PT correlation, and this has been done in the past, roughly 10 years ago, for the second order correlation of dynamic correlation between PT and PT. And recently, there's a new paper from Zhang Yong and collaborator published in PRC about high order transverse momental correlation between 3 different particles or between 4 different particles. So, and also in this seminar, we try to present the first study of the correlation between VN and PT, and to really show you a new, an additional insight into the initial condition. And such information cannot be obtained if you just study PT correlation, or if you only study the azimuthal angle correlation. In terms, if you think about the draw, the V2 PT correlation. Now the question is, can we also extend such a study to the high order cumulant between PT and VN? Can we study the multiple flow coefficient with PT correlation, or can we also study higher moments of PT with VN coefficient? So one of the recent examples have been made in Alice is the correlation between mean PT and V2, V3 at the same time. So what we see is, if you look at the black points, it's a centrality dependence between V2, V3 and mean PT. It is negative for the entire centrality up to 50%, while most of the data somehow with a very large uncertainty can follow the trend. But then it has been noticed that if you only look at IP plasma plus music plus ULKMD with final state effect only without CGC, it shows a very strong centrality dependence and change from positive to a negative sign, which is very different from their own calculation for the full evolution of IP plasma plus music plus ULKMD with CGC. And again, what we do not understand at the moment is, can we interpret such a difference between FSE only and the full IP plasma simulation as the potential CGC effect, or can we conclude from the current comparison between data and IP plasma that CGC is needed to describe the data? I think a lot of things has to be understood in the near future. But again, if you just look at the current uncertainty of the theoretical model, it is still very large. So this sizable uncertainty will really stop us to draw a strong conclusion of this comparison. Even the data itself is almost very precise. So this brings me to the summary. So here I try to show you the developments of the multi-particle correlation in the last almost 2 decades. We start from multi-particle azimuthal angle correlation, which have been used in many of the standard flow studies. And those results can be used to probe both event by event geometry fluctuation as well as extract the properties of QGP, including both shear and bulk viscosity as function of temperature. The state of art, if we still put it this way, can be done based on these Bayesian analyses, right? And in addition, we also discussed a new horizon for the correlation between V2 or the Vn and APT by introducing the PT correlation to the multi-particle correlation, which gave us a direct access into the initial condition, which was very poorly known in the past. And for the first time, we see a completely different result between IP plasma and Trento based on based calculation. And what we know is the size of the nucleon is definitely matter. And this might already connect the current LHC measurements to the future EIC measurements, because they really show you the information about the nucleon size within the ion. But then we still need to understand what's left, what's else in addition to the difference between IP plasma and Trento. Are there any dependence on thickness function or pre-hydrodynamic flow or some other effects? So I guess that's it. And thanks for your attention. Any questions are welcome.
Well, thank you, Yu, for this wonderful talk on the experimental summary of this current state-of-the-art studies of correlations. So I guess if you have any audience, if you have any question, please raise your hand or just unmute the mic and ask question here directly. Let me see. Well, let me ask a couple questions before others people are raising their hand. If you go to the page 11, where you look at the normalized correlation, So I understand that if you do this, if you look at the correlation between 3 and 2, and especially if the viscosity probably only affect the coefficients between the correlation between the V2 and the epsilon 2. So that's why, and then this normalized symmetric cumulant sort of cancel out, and then you only are sensitive to the initial condition. Mm-hmm. Why actually this does not happen for this correlation between cumulant 2 and 4 and 2?
Yeah, very good question. It's because V4 is not nearly correlated to epsilon 4. So V4 is a little bit more complicated. It has both the contribution from epsilon 4, but also the contribution from epsilon 2 square, what we call the nonlinear hydrodynamic response. So if you plot within the hydrodynamic model V4 as function of epsilon 4, you will find some nonlinear relation.
So this is essentially because of the V4 is not really linearly proportional to epsilon 4.
Yeah. So if you already look at V2 and V3 in peripheral correlation, you will also see the deviation between the final state and initial state in model, as you can see here for AMPT.
Yeah.
It's because V2 and V3 also have nonlinear response in more peripheral correlation.
Yeah. I see. Okay, let me hold on my question first. I have a couple of other questions, and Matthias, please go ahead.
Yeah, I'm sorry, I just got a phone call in the meantime, but you stopped at the right slide. So a silly question, and I think you started talking about this. So the deviation, that the fact that the AMPT seems to be hopeless even at 40% is the nonlinearity of the physics there, or is that right? And AMPT is just cannot make up for it with whatever they do with the cross section of the partonic interactions. And
yeah, I guess at that time I think for theoretical model calculation we were not very careful for the static uncertainty. So if you really plot precise static uncertainty with the bootstrap instead of just row calculation, I think this uncertainty is a little bit underestimated.
I
so
see.
It's my impression. So you also have these bin by bin fluctuation at that time.
So it would be closer to a 1 sigma difference.
Yeah, it will be. I think it will be closer, but then you would expect some deviation when you change.
No, I think it has to break down, right? It has to diverge.
Yeah, they should.
Yeah, larger centralities. Okay, thanks. Very nice talk, by the way, Yo. Thanks for being here.
Okay, anyone else have questions? This Giuliano gave a talk last week on this. So he also mentioned about this correlation between PT and VN, in particular, the effect of the geometry essentially. So if you go back to 23, and you mentioned there is a really difference between the I-Plasma and Trento initial condition. I vaguely recall that he thinks this is really because the size, the nucleon size are very different in these two approaches, right?
Well,
because of
that's indeed supported by both left-hand side calculation and right-hand side calculation. So left-hand side is basically the initial state from different model, and again with different nucleon size from 0.4 Fermi to 1.1 Fermi, and it follows this trend. And while in the right-hand side, it's within IP plasma with different nucleon size. But my question is, besides such a dependence on the nuclear size, is there any remaining effect? And I can already tell there will be, and there must be a remaining effect if you look at the transition calculation. So if you look at blue, there's a decrease and then increase. So even we consider this error bar, there's a still increased trend. And we in fact also checked in the initial state calculation. That's
only
just coming from this particular model, like, right? Trajectory. Right?
Yes, it's because only in this trajectory calculation, they consider some pre-hydrodynamic flow, or called free streaming. Free streaming. So this free streaming might play some role in more peripheral calculation. And I think for the other calculation like VHP hydro or Jetscape, if they want to try, they can just introduce this artificial limit and then see if they can get a similar trend. And in addition, so in the right-hand side, they also have the size of there's also different consideration of the nucleon structure. And this hasn't been done in Jetscape. While for some of these initial Duke Bayesian analysis, they have these 4 to 6 constituents in the Trento calculation. So that might also play some role. So that's what I'm saying, that besides the effect from the nucleon side, there could be additional effects that we do not fully understand yet.
Yeah, I see. And for that matter, do you think that looking at the small systems can give you more like information about nucleon size issue? Have you
yes,
kind of correlation is in particular the PT versus VN correlation for small systems like proton nucleus?
Yes, very good question. In fact, we did most of the study with the system size scan, and my group also did this oxygen projection study for this rho V2 PT, and it's because IP plasma claimed that there will be twice of the sign change as function of multiplicity, and this Giuliano might mention that as well, due to the interplay between hydro part and the CGC part. But the question is, if you are going to smaller and smaller collision system, the initial state fluctuation will be stronger and stronger.
Yeah.
In a sense, the fluctuation might wash out the geometrical effect or the geometry effect and change the whole idea behind the size and the geometry correlation.
So from there, you have to really get a good handle on the fluctuation first.
Yes. So one of the idea we had, and let me see if I have this in the slide. So one of the idea we have is try to use the correlation between VN to probe the nucleon size and the nucleon, the deformation parameter that he might also talk about. This has been done in xenon-xenon collision, that we can have the sensitivity of the LHC data to probe the triaxial structure of xenon 1 to 9, and also try to constrain the beta 2 parameter in the central collision. But now, if you move to smaller system like oxygen, that we did in Alice a lot of careful systematic study for the projection for the future. None of this ever considered the structure of oxygen-16, which means, is it the alpha structure, alpha clustering structure? How do they play this alpha, with a Y shape or with some other shape? For all of this, it's unknown how to implement it in the current initial state model. While I have to say, for low energy nuclear structure study, this has been studied extremely well. And one of the proposal that Giuliano and I try to have in a coming, well, later this year, is we try to collaborate the high energy heavy ion physicists to the low energy nuclear structure physics to see if we can use their expertise to implement such a initial state, such a geometry or such a nuclear structure in the current initial state model, and to improve our prediction for coming oxygen run, or also for the isobar run for the rig.
I see. Well, good. Well, thank you very much. I think if there's no further questions, I want to thank you again for this great talk. It's a really nice talk. Thank you so much. Okay. Bye-bye, everyone, and see you.